Welcome to the second part of stereoisomerism. In the first part, we have seen the definitions and related concepts. In this part, we will see the stereochemistry of cyclohexane. Cycloalkanes are the compounds which are obtained from closing the rings of open chain alkanes. This is cyclopropane with 3 carbons. This is cyclobutane, cyclopentane, and cyclohexane. This is the open chain structure of propane, which has 3 carbons, and we know that this carbon is sp3 hybrid, and the bond angle should be 109.5 degrees in a saturated sp3 hybrid carbon. When we want to make a ring and join these 2 carbon to make cyclopropane, then basically we have to bring these 2 methyls close to each other so that they can have a bond formation between them. But when we are bringing these methyls close together, this bond angle is supposed to change. So here what we realize that the bond angle is supposed to be changed in order to make a ring structure. These observations were studied by Baeyer, and he gave us a concept of angle strain. Definition wise, angle strain is the deviation from normal bond angle. The ring size increases from 3-membered ring, it becomes 4-membered ring, and the angle strain decreases. Similarly, when we go from 4-member ring to 5-member ring, 5-member ring, the angle strain further decreases. However, when we go to cyclohexane, the angle strain further increases. All cycloalkanes are planar. In order to make cyclic compounds, bond angles are deviated from normal value. Deviation of bond angle causes angle strain in the ring and makes it unstable. The larger rings are difficult to make because they are highly unstable due to larger angle strain. So these are the assumptions of Baeyer strain theory. In order to validate this Baeyer strain theory, we do have some data to support these assumptions. That data is in the form of relation between angle strain and stability of cycloalkanes. Here is the list of molecules: cyclopropane, cyclobutane, cyclopentane. Internal angle is given, and we have this angle strain for each molecule. And here we have heat of combustion for each CH2 of our cycloalkane in kilocalories per mole. As you see, angle strain is 24.75, and accordingly the heat of combustion is 166.6. Angle strain is decreasing down, and so as and heat of combustion is also decreasing down. The angle strain further decreases down, and here the heat of combustion also decreases. However, we have one anomaly, that cyclohexane angle strain is increasing from cyclopentane to cyclohexane. This is cyclopentane angle strain, this is cyclohexane angle strain. So we are expecting that this value of 158.7 should further increase for cyclohexane. But what has been noticed is that the Cyclohexane molecule has heat of combustion for ECH2 in the range of 157.4 kilocalories per mole. This heat of combustion is equal to the heat of combustion in open chain compounds. And we know that in open chain compound there is no angle strain. Therefore, it appears that even cyclohexane ring has no angle strain, and this value of angle strain is not in agreement with the heat of combustion value. So here are the two observations. The data shows that molecule with lesser angle strain has lower heat of combustion and consequently they are more stable. However, cyclohexane has lower heat of combustion despite greater angle strain. Do remember that angle strain here is calculated as per bare assumption of planarity of the ring. The cyclohexane structure is supposed to have a regular hexagonal geometry. Shortcomings of Baeyer strain theory. Baeyer strain theory is applicable to only smaller rings of 3, 4, and 5 carbon atoms. We see that angle strain values and heat of combustion values are in agreement. Angle strain decreases, heat of combustion also decreases. Larger rings are stable and they do not have angle strain. This is the shortcoming of the theory, that it is applicable to smaller rings, but it is not applicable to larger rings. Contrary to the assumptions made by Baeyer, rings with more than 5 carbon atoms are not planar. This is the observation which is known to us in recent times, that all the rings are not planar. As we know that when we increase the number of carbons, the ring becomes more flexible and it does not remain planar. So the cyclohexane ring, which we were assuming to be a planar structure, is in fact flexible system because of more number of carbons, and these carbons are going up and down in such a way that they give rise to this kind of a structure where all the carbons are not in the same plane. Some are above the plane and some are below the plane. So it gives rise to this kind of flexible structure which appears to be like a chair form of cyclohexane. First we will learn how to draw this chair form of cyclohexane. I will show you how to draw two structures together. One will be a chair, the other will be the mirror image of the chair. So you draw two lines which are parallel to each other, but they are not starting from the same level. This line is more towards on your left and this line is more towards on your right. So they are not at the same level. Similarly, these two lines are parallel to each other, but this one is more towards your right and this one is more towards your left. Once you draw these two lines, what you are supposed to do is join these two lines with a point like this. And then similarly, these two lines from this side are joined to a point somewhere like this. This gives us two structures of chair form of cyclohexane, which are mirror images of each other. We are supposed to learn the position of hydrogen atoms in cyclohexane, how to place the hydrogen atoms. For this, we should differentiate the 6 carbons of cyclohexane in upper and lower carbons. As you see that this carbon is in the upper position than this carbon. Okay, so one thing you can notice is that these carbons are alternately up and down. This is up and this is down. This is up and this is down. Okay, so we have three red carbons which are in the up position and three blue carbons which are in the down position. What we will do now is on the upper carbon, we draw a vertical line to place one hydrogen. This hydrogen is vertically drawn, it is known as axial hydrogen. And similar to this carbon, we will put two more hydrogens vertically aligned. So these are three axial hydrogens on the upper carbons. On the lower carbons, we will also draw, on the lower carbons, we will draw axial hydrogen in the down position. They are going down. So we have got these six hydrogens which are axial hydrogens. Now we will put the other hydrogen on each carbon. For that, you take care that the bond angle is maintained in such a way that it appears to be almost 109.5 degrees. You take care of one point is when you are going to put the second hydrogen, you take care that when one hydrogen is going up, then the other hydrogen will go down. Okay, similarly, this hydrogen is going down, so the other hydrogen goes up. So on the same carbon, no two hydrogens are going in the same direction. They are always traveling in the opposite direction. Okay, we place the remaining hydrogens. These two were going down. So now it is going in the upward direction. Similarly, these two are going up. So their counterparts will go in the downward direction. This is how we are supposed to place these hydrogens. So the green hydrogens are called as equatorial hydrogen atoms. The vertically placed hydrogen atoms are called as axial hydrogen atoms. The hydrogens which are above the plane, like this hydrogen, they are called as beta hydrogen. This hydrogen is also beta because it is traveling in the upward direction. They are called as beta. Okay, this hydrogen is going in the downward direction, so this is called as alpha. So this is also alpha and this is also alpha. So there are six alpha and six beta. Similarly, there are six axial and six equatorial. This is another view of the three-dimensional structure of cyclohexane in the chair form. So this has formed because the ring is flexible. Now what we are going to learn is how to convert this structure into a Newman projection formula. Cyclohexane in Newman projection. This is the Newman projection of ethane molecule. We will try to put cyclohexane ring in this kind of Newman projection. When you draw chair conformation of cyclohexane in Newman, this is what it will look like. And we will learn how to draw this structure. This is the three-dimensional structure of cyclohexane. It has the carbon atoms have been numbered like 1, 2, 3, 4, 5, and 6. When we want to draw Newman, we want to have this carbon number 3 and carbon number 5 in front of us. For that, what we can imagine is the rotation of this ring, like this. I am repeating it again. So we are rotating the ring in this fashion. So we get this carbon number 3 and 5 in front of us. And behind carbon number 3, we have carbon number 2. Behind carbon number 5, we have carbon number 6. And all these lines are nothing but connected to hydrogens. This carbon number 3 will be shown as a dot and carbon number 2 will be shown as a circle. This will be shown as a dot and this will be shown as a circle, and we will join them. So this is how it looks like. Carbon number 3 is, this is the carbon number 3. This is carbon number 2. This is carbon number 5. This is carbon number 6. Carbon number 6 goes to carbon number 1. So this is carbon number 1. And this is carbon number 4. So this is the chair form of cyclohexane in Newman projection formula. Drawing of this structure more simple, what we can do is we can take a staggered form of ethane and we take its mirror image. Then we bring these two structures close to each other. And when these two hydrogens are overlapping, this will give us a CH2. And these two hydrogen will also give us a CH2. And this can simply give us our cyclohexane structure in the Newman projection formula. Cyclohexane is a flexible structure, and this flexibility gives rise to different conformational forms in cyclohexane. We are going to study these conformational forms or conformational isomers. This is the cyclohexane ring, and basically this ring is flexible. So what is happening here is this lower part has come up, and what we are getting is a different form of cyclohexane. So the chair form has changed too. As you can see, this part is coming up slowly. So this is half chair form. So this is half chair form. Now this part, if it goes further up, we get a boat form of cyclohexane. So this structure looks like a boat form. Then this boat is getting twisted, so we get a twisted boat form structure. So basically cyclohexane exists in 4 different uh, conformational isomeric forms. So there are 4 conformations of cyclohexane. This is half chair, this is boat, this is chair form, and this is twisted boat. Now we are going to study these 4 isomers and their potential energy in some more details. Conformational isomers of cyclohexane and their energy. Chair form. In the chair form, all the hydrogens are staggered. As we see from the Newman projection, these hydrogens are away from each other. They do not have any kind of torsional interaction. In addition, since the ring is flexible, it has adjusted in such a way that there is no angle strain. So what we notice in this structure is there is no torsional interaction. In addition, there is no angle strain in this form. Therefore, chair is supposed to be the most stable conformational form of cyclohexane, and its potential energy will be almost equal to 0. Board form. In the board form, this is the board form, and if we look from this side, in the Newman projection, it will appear like this. And what you notice here is the hydrogens are aligned together. The dihedral angle between the hydrogen is zero. This gives rise to torsional interaction. There are four pairs of torsion interaction in this form. In addition, what you see here is these two hydrogens are very close to each other, and the space to accommodate them is only 1.8 angstrom. So available space is 1.8 angstrom. However, the sum of van der Waals radii of two hydrogen atoms is 2.5 angstrom. It means that it is the minimum distance they can be brought together so that they will not have any repulsion between them. But the available distance between them is 1.8, so obviously there will be repulsion between the atoms and they will repel each other and the energy of the molecule increases. So the torsion interaction and black hole interaction increases the energy of the molecule by 7.1 kilocalorie per mole, half share. This is the most unstable conformation of cyclohexane. In this conformation, there are large number of pairs of eclipsing hydrogen, as you can see from the three-dimensional structure. These two hydrogens are aligned together if you view from this side. Similarly, many pairs of eclipsing interactions are available in this half-share form of cyclohexane. In addition, certain amount of angular strain makes the molecule unstable. The potential energy of this conformation is 11 kilocalories per mole. Twisted boat. Here what you have is a regular boat and this is the twisted boat. Main noticeable difference is the distance between these two hydrogen is less. When you twist the boat, these hydrogens are going away from each other. That is one observation which is very much notable. The other observation is hydrogens are eclipsing in boat form, but when we twist the boat, then the hydrogens are not eclipsing with each other. So the dihedral angle between them increases. Keep these two observations in mind and let us go to the description. To decrease the flagpole interaction, the C1 and C4 are taken away from each other and the shape of the boat is slightly twisted. This form is called as twisted boat. The energy of the molecule is 5.5 kilocalories per mole in this conformation due to partially eclipsing hydrogens on adjacent carbon atoms, causing lesser torsional interaction. So here we have completed the conformational isomers of cyclohexane and their energy.